Get set go.
Yeah, so good night, everyone, or good evening. So, uh, I will be talking about Green's functions today, and these play a very important role in physics. And I'll try to sketch their importance while not boring you with mathematical details much. So, let us begin, and that is why the background is green because I'm talking about Green's function. Although it's actually a name of a British mathematician, Joseph Green. So, a simple question is we know that there is something called as a derivative operation. So, what is the inverse of a derivative? We know it's an integral, but if you think in terms of matrices, for example, if you have a square matrix A, then the inverse of that square matrix A is defined through AB equal to identity. So we call B as the inverse of A, correct? And that is how you define even for numbers. For example, A times B is 1, then B is inverse of A. So similar thing will happen here. You will think of these derivative operators as basically matrices that will act on this g of x to give a delta of x, and this delta of x is like the identity in the functional space. If you have doubt about this, I can explain you on my tablet later, and you can ask me question at any point in the time because I want it to be interactive because I don't have many slides today. So yeah, so what do I mean by derivative operators? It can be any polynomials of these polynomials, or not even polynomials. It can be square roots also. So it can be d by dx, d square by dx square, d by dx raised to or square root of d by dx, d by dx square plus 4. All these are derivative operators. What do I want to do is I want to find the inverse of these operators. So these derivative operators act on functions, and these functions are a part of vector space, which we call as a functional space. So you can think of the matrix analogy. These derivatives are nothing but matrices acting on vector space, which is the functional space. And now what I'm asking is, what is the inverse of this derivative in this functional space? So all this sounds very mathematical and boring and all these things, but it has very nice physical significance, and we'll get to it once we look at some very interesting examples. So is there any question at this point?
निपुण तू स्क्रीन शेअर केली आहे का?
हो, केली आहे. विश्वासनी
अरे
काय? आय थिंक विश्वासनी पिन नाही केलाय मला.
आणि देवेंद्रने हँड रेस का केलाय?
Pin I. I think the screen is visible and it is also pinned in my
नाही,
screen.
बट एक मिनिट. नहीं
हाँ
यार,
देवेंद्र बोल.
दिसतंय का?
स्पेस क्या है?
हाँ ठीक है. सबको प्रेजेंटेशन दिख रहा है ना लेकिन?
यस यस.
Yes.
हाँ.
अरे दिसतंय
फंक्शनल
तुम्हाला?
Yes, refresh कर श्रेयस नाहीतर एक्झिट करून जॉईन कर.
एक
हाँ, फंक्शनल स्पेस क्या है, ये क्वेश्चन पूछा ना देवेंद्र ने? हाँ, functional space is like a vector space only. It is basically spanned by basis vectors which are functions of x. Okay, for example, you can have 1 comma x square comma x cube. These are like the basis for any polynomial, correct? Any polynomial is a linear combination of these: 1 x square x cube x to the power 4, and so on. So this is infinite dimensional vector space, and 1 x square x cube x raised to n, these are basis vectors. You can multiply them by real coefficients or complex coefficients and form a polynomial. So any polynomial which is like a vector in this space can be written as linear combination of 1 x square, etc. So that's why this functional space is just like a vector space. Like in 3D you have I, j and k. These are the three basis vectors. In functional space you have infinite of them. Okay, clear है? Hmm. So base same analogy, a matrix You think of derivatives or the derivative operators as matrices, and you want to find the inverse of these matrices, and this inverse of these derivative operators rather are called Green's functions, and they satisfy this equation, which is dg of x equal to delta of x. Delta of x is like the identity in the functional space. Okay, so let's move ahead. Yeah, so why are they important? So they actually help us to calculate the nature of force laws in fundamental theories of interest like gravitation, electromagnetism, etc. So for example, you know that if you place a charge at the origin, then the potential, say x distance away from the charge, is 1 over x. It is q by 4 pi epsilon naught x. How do you know that it is q over 4 pi epsilon naught x and not q over 4 pi epsilon naught x cube or x n or sine of x, cos of x? Why is it not that? So the question is very fundamental actually. The nature of force laws is actually dictated by the Poisson's equation, which we solve in for gravitational potential and electromagnetic potential. So del square phi equal to rho. You can think of phi as a gravitational field, then rho will be like a matter density. If you think of phi as a electromagnetic potential, then rho will be like uh, charge density. Okay, so when you solve this equation in 3 dimensions for a single charge, so instead of a charge density, just place a single charge at the origin and solve this Poisson's equation. But this is exactly the definition of Green's function. So when you solve for the 3 dimensional Green's function, this del square g is equal to delta 3. So there should be a 3 here, which means it's a 3 dimensional delta function. Then what you get is g of x equal to 1 over x. And that actually tells you the behavior of the potential. And from potential, you can obtain force. Correct? So this equation, del square phi equal to rho of x, this is a very fundamental equation. This actually tells you the relationship between the potential generated by a matter or charge distribution in a given space. And further, this is sensitive to the dimension. So actually, the nature of the force law is dimension dependent. It's not the case that if it is 1 over x square in 3D, it will be 1 over x square in 2D or 1D. So in each dimension, you will find that the nature of force laws for these theories like gravitation, electromagnetism, etc., is different. So the way you actually test what dimension you are living in is by doing experiments which will actually tell you what is this force law. If this force law is like 1 over x, you know that you are living in 3 dimensions. If this force law is like 1 over r raised to 8, then it means we are living in 10 dimensions, and so on. So this is an important part. So I hope I was clear here. Is there any question?
हॅलो.
Ha, hello.
म्हणजे फोर्स फ्लो डिपेंड्स ऑन डायमेन्शन. मग सपोज इफ देर आर 4 डायमेन्शन्स,
Correct.
तर त्याचं रिलेशन कसं असेल?
Now here there is a catch. When you say 4 dimensions, actually you have to specify whether you are talking about 4 spatial dimensions or 3 space dimension and 1 time
येस येस
dimension.
येस, 4 स्पेशल.
If you have 4 spatial dimension, then the potential will go like 1 over x square rather than 1 over x. Okay.
ओके.
So you can solve for this equation del square g equal to delta 4, because now this will be 4 dimensional delta function. And you can solve this equation using techniques of Fourier transform, which I can show later on my tablet. It's 2-3 steps. We can do that. And yeah, so you will find that it is 1 over x square rather than 1 over x. So actually the potential damps faster in 4 dimension than 3 dimension. So even the force is sensitive. If you compute force out of this you'll get 1 over x cube dependence, correct? Because force is nothing but derivative of potential, correct? So you will get 1 over x cube.
Okay.
And in 3 dimension the force is 1 over x square. So you see how the force is behaving in different dimensions.
So that means we can simulate the force.
What do you mean by simulate?
Means we can make a simulation. Means how force will behave in fourth dimension, fifth
Yes,
dimensions.
yes. You can make a simulation. In fact, I have in I have prepared some simulations uh, on in Python using the turtle model. So you can put these kind of potentials: 1 over x cube, 1 over x raised to r, logarithmic. Try all kinds of forces. Sorry, and simulate, let's say, system of two particles, how they behave, what are the trajectories of these particles. It's actually interesting. You can try this.
So I heard strong force is directly proportional to distance.
No, that is
Is
actually not the case, because you know that it has a limit beyond which it becomes negligible. So,
okay.
yeah, so it actually is influential in a
So
certain neighborhood, and outside it, it is zero. It's like potential well, finite square well, or spherical well. So, if you take a sphere, so inside the sphere there is some potential, but outside the sphere it's zero.
okay,
So this is like a model of nuclear potential.
means it is applicable for only central forces.
For yes,
Central
this
forces.
this formula del square phi equal to rho of x. This
Okay.
is true for gravitation and electromagnetism. I'm not talking about strong and weak force here. Strong force is, as you said, it is proportional to x, but when x is very small, because nearest neighbors grow over certain region, and after that the neighbors are almost constant. So it's not sensitive to large distance variations in x. Only in very small x the strong force grows, but it's very strong in that region. It dominates
Okay.
all other
Okay.
forces. But I don't think there is a uh, what you can say, there is an actual f of r kind of force law for strong force which has been found. Like for gravitation, you can give 1 over r square. For electromagnetism, also it's 1 over r square. But for strong force or weak force, I don't know how. What is the compact form of this f of r force? Probably there is no closed form for this. Yes. No relativity, nothing. Simple. Time is just a parameter. It runs the same way for all observers. We are in 3D, and this phi is non-relativistic, simple gravitational or electromagnetic potential, and rho is like charge density or matter density, whatever. If you're solving for gravitational potential, rho is matter density. If you're solving for electric potential, it is charge density.
Okay. That means no fancy terms are involved.
No fancy terms. Simple.
Okay.
So this actually tells you what is this equation here. This is the definition of Green's function, but it is also telling you that if you place a charge at the origin, what is the potential generated by that charge? And that potential is actually the Green's function. And we know in electromagnetism that if you know the formula for potential generated by a charge at a distance x, then you can actually find for any random distribution, correct? You will just sum over contributions of these dqs in your charge density, uh, and get the full potential, correct? So what this tells you is that you just solve for the Green's function. When you solve for the Green's function, you have actually solved for any problem of electrostatics. Give me any rho of x, I can actually find the potential generated by this rho of x, correct? Yes, for gravity, it's like a point mass placed at the origin. For electrostatics, it's a point charge placed at the origin. So you just find what is the potential due to these point mass or point charge, and then you can find it for arbitrarily extended bodies, charged or uh, basically massive bodies, because you can sum over contributions of those infinitesimal charges or masses, sum over that entire body, you will get the net potential generated by this extended object. Correct. So this tells you that Green's function actually contain a lot of information. You just solve this one equation, you are able to do many things with it. So it's really important. And another important point is that it's sensitive to dimension. And it's a very good coincidence that we live in 3 plus 1 dimension. Uh, and if I get time, I will talk about this at the end of my talk. Okay. Yes. So let's start with very simple cases. So actually, I am not going into very mathematical details of Green's function, because the way it's introduced in textbooks, and it's very boring, and it has a lot of boundary conditions, initial values, and all these things. But it's not necessary for the purpose of this talk. The important point is to know the physics of this Green's function. Mathematical details I can give for anyone who is interested in learning about this. So for the purpose of the talks, this will be very simple hand wavy calculation, stressing on the physical aspects more. Yes, I'll shift it up. Yes. Now let's start with very simple example. What is the simplest derivative operator? It is just d over dx. So let's solve for d over dx acting on g of x equal to delta of x. What is g? The answer is very simple. It's the step function theta of x. This exercise many of you might have done in quantum mechanics. Derivative of theta function is delta function. So d by dx of theta of x is delta of x. So g of x is nothing but, so this is a typo here. This should be theta of x here. So the Green's function is the step function. What is step function? Step function is basically 0 for x less than equal to 0, and it is 1 for x greater than 0. So you see that there is a jump at x equal to 0. Therefore, when you compute a derivative at x equal to 0, you get infinity. And that is precisely delta of x. For x strictly less than 0, delta of x is 0, because derivative of theta function will be 0 for x strictly less than 0, because it's just constant. And similarly, for x greater than 0, also derivative of theta function will be 0. Similarly, delta of x is also 0 for x not equal to 0. But at x equal to 0 is infinite. So it's intuitive, right? That derivative of theta function is delta function. So the Green's function is what? It's just the step function. Now, if you remember Griffiths, then there is a problem of finding wave function for this potential. I think it's a scattering problem. So you can find, you can basically uh, extract the physics out of it by solving for the wave function for this potential. But classically also you can think about this problem. If you have, let's say, a system whose potential is like this, it's a step function. Let's say at x equal to 0 there is some potential, and this potential is at that value for x greater than 0. And if a particle, let's say, approaches with certain energy, will it be able to cross this potential or not depends on how much its energy is, right? If its energy is greater than the barrier, then it will cross it. If it's not, then it can never cross that. It doesn't have enough energy. Correct? This is the classical picture. Is there any question? Yeah. So this is just the classical picture, but you can also do quantum mechanics with this. Solve for the wave function, extract probability amplitudes, reflection or transmission amplitudes, reflection amplitudes, and so on. But this is the very simplest example, theta of x, which is the Green's function for the operator d by dx. Okay. And you can think of this g of x as a potential. for a classical particle. And you can also again simulate, as Shreyash pointed out. You can do simulations with this and try to find what is the dynamics of two particles in which have a potential like theta of x between them. Okay. Hmm. Correct. Correct. So, so if you think of this equation, d by dx acting on g equal to delta of x, actually, if you really think in the formal sense, inverse of derivative is actually integral. It's not a function. Correct. Here, what am I defining is d by dx acting on g of x equal to delta of x. This g of x is a function, but it is also like a matrix. You think of it like a matrix which can multiply a vector in the functional space. So finding the inverse of that operator, like in the previous case, this del square, what it physically does is actually it tells you the propagator of the system. Propagator or correlation function. That's the right word. It tells you how 2 points are correlated. 1 over x, 1 over x square, 1 over x cube, etc. So the inverse of this del square, because this del square phi equal to rho of x is actually in the field theoretic sense, classical field theory, this is one of the Maxwell's equation, right? One of the four Maxwell's equation. So so this is actually solving for the Maxwell's equation itself, but with a delta function source in this case. And this delta function source actually tells you the correlation, or rather the dependence of the potential on the distance between 2 points. And once you know this, you can find the potential, or you can solve any electromagnetic system given any rho of x. Does that answer your question, or you had some different question? I answered something else. I like to think of it as a correlation. You won't find this anywhere, but I try to build this analogy with correlation uh, because this is actually like a 2 point function. When you find inverse of some derivative operator, this what is this derivative operator? This is actually telling you the dynamics in the system, right? This del square phi equal to rho of x is telling you what the system is doing. Means if I place uh, so there was a charge at the origin. If I place a charge somewhere x distance away, this will actually tell you what kind of force will be there between these charges, and hence what will be the dynamics of this system. Correct. So this derivative operator actually contains the information of the dynamics. But what you want is not, you are given rho, you are not given phi, you want to find phi. So it's like taking this del square down in the denominator, and taking that del square down in the denominator is just like the Green's function. Okay, it's like phi equal to 1 over del square rho of x. So this one, yes, exactly, that is the solution. There is an integral, but roughly that's the answer. Yes, correct. So okay, so this is the simplest case. Now let's complicate the problem. Instead of one derivative, let's take two derivatives. So you have d square by dx square g of x equal to delta of x. How to find g? So you see, this is just a one-dimensional system. If x is not equal to 0, you know that it's just d square by dx square g equal to 0, which means g can at most be linear. But you see that it actually does not give you the solution for the required differential equation, which is delta of x, because at x equal to 0, g of 0 is actually b. It's not divergent in that sense unless you actually put b to be delta of 0, in which case it is divergent everywhere. So actually it does not make sense, but what you can do is you can remove that point x equal to 0, which also doesn't make sense, but still I would like to do that. And what intuitively is happening is you see that this Green's function, or whatever you would like to call it, modified Green's function, it's actually growing linearly with x. So if I have a charge place in one dimension, there is only one dimension, there are no other dimensions, there is just one charge place on a line, then the potential is actually growing with distance, which is like counterintuitive to what we have in 3D or higher dimensions. Potential usually falls off as we go away from the charge, but here the magnitude of the potential is actually growing with distance. In fact, the far apart you are, the higher the potential is. So one way to solve this problem is actually put it in a box. In 1D, you say that you are working on a in a box rather than the full infinite space. So then this problem of infinity will be solved, but still there is a problem at the origin. You cannot find g of x actually which works. Putting putting in a point means that, sorry, you put boundary conditions on the g of x. You say that g of, let's say, 1 should be 0. Okay, so what does it give you? A plus b equal to 0. And similarly, you give another boundary condition. Let's say at x equal to epsilon. Because at x equal to 0, it is actually divergent quantity and it's not defined. Means, see, if you put x equal to, if you differentiate this twice, you always get 0, is irrespective of whether x is 0 or non-zero. Correct. But what you want is at x equal to 0, you want a divergence. Correct. Which you are not able to get from this linear function. So what I'm saying is, forget about that. Forget about that point. Just look at it close to that point, epsilon, where the g of x is still 0. And then you will be able to actually find this g of x. Put some boundary condition at g of epsilon. Put it to be some finite number. X is epsilon. I am saying put g of epsilon to be some finite constant. So you will get, not divergent. So you'll get two equations. One is a plus b equal to 0, which I put g of 1 equal to 0. And other will be some a plus b, a epsilon plus b equal to something. And then that will fix a and b basically up to some epsilon. But the important point is here the potential is actually growing with distance. You see, and that is what I am stressing on here. That what when I say physics is dependent on dimensions, because the nature of the dynamics is sensitive to the force law, and the force law is governed by the potential. And you see, the potential is actually the solution to the Green's to the Poisson equation with delta function as a source, or rather the potential itself is the Green's function, and Green's function depends is dimension dependent. So the entire physics is related to what the Green's function looks like in any D. So if you go to 2D, for example, you will find that the Green's function is logarithmic. Correct. So what this tells you, what will be the force? Force will be like 1 over x. So in 2D, the force is 1 over x. In 3D, the force is 1 over x square, which is the Coulomb's law, or the gravitational Newton's gravitational law. Correct. In 3D. So g of x equal to log of x. So you can try this problem. Try to find this del square g equal to delta 2. Find this g. This should be equal to log of x in 2D. Okay, this is very easy to do using Stokes theorem. So let me quote a result in arbitrary D. So in arbitrary D, you have 1 over x. This potential to be 1 over x raised to d minus 2. So put d equal to 3. You will get 3 minus 2, that is 1. So potential is 1 over x, which is what we expect. In 4, as Shreyas asked, it is 1 over x square. And as you grow the dimension, basically it will become more powers of x in the denominator. Can you repeat what you said? Curl. Hmm. Del cross E is 0. No, but del cross E is only 0 if B is 0. There is no magnetic field. If there is a magnetic field, then you know that del cross E is minus del B by del T. Correct. Correct. No, you can. So, are you saying that curl is only defined in 3D? Uh, there is no curl in 1D. There is. You can define a curl in 2D. Ah, ah, yes. Hmm. You can think of it like that. Yes. Mm. Even also in one dimension, you see the potential is linear. If the potential is linear, what is force? Force is derivative of potential, which means it is constant. So no matter what the distance between two charges, the force is always constant. So this also you can simulate in. So if you place two charges in one dimension and there was no other dimension ever, then these will continuously be pushed away with the same magnitude. Correct? In 2D, you see the growth of the potential is lowered because log increases the speed of uh, growth of log function is smaller than polynomial function. Log function grows very slowly. So potential grows very slowly in 2D, but it still grows as x increases. But when you go to 3D, suddenly what happens is as you move apart, the potential starts dropping. The nature of the potential itself becomes 1 over x. So as you move apart, the potential starts dropping. Okay, and somehow we seem to live in three dimensions, and it has such nice behavior that it is 1 over x. That is, the force decreases with distance, and this is, I think, partly the reason why we can actually solve problems. If the force was going to increase with distance, everything will be divergent, right? Because things will go apart and apart, and this process will just go on forever. So there will be no bound state at all. So yeah, this my talk is pretty much over. So let me quote some thing as I always do. A man is like a fraction whose numerator is what he is and whose denominator is what he thinks of himself. The larger the denominator, the smaller the fraction. Which actually makes sense. And there is, so wait, what happened here? There is a quote by Bhaskaracharya on infinity, uh, which tells you that if you multiply anything by 0, you get a 0. But if you divide something by 0, then it's infinity. And there is one more, which explains that if you add something to infinity or subtract something from infinity, infinity is unchanged. Yes, I believe in it because they are right there everywhere. Infinity is always there.
Why?
Simple example, take point particle. What is the gravitational force between two point particles? It is gm1 m2 by r square. What happens at r equal to 0? No, if you take point particles, r can be 0, right? Infinity is always there. Infinity, you cannot escape infinity.
I Vishwas doesn't believe in infinity.
Nay, that is true. But let's say you have a circle of radius 1. I tell you count the number of points on the circle. It will be infinite. But let's say I make some segments and I count it. Let's say I give you a circle of radius 2 and I ask you to count the number of points on the circle. You know, in both cases, the number of points is infinite, but you can still compare. You can still say that the number of points on the circle with radius 2 is greater than the number of points on the circle with radius 1. Both are infinite, but still you can compare. So actually, infinity is not that. Uh, what I should say. It's not so. I can't find the right word, but it's infinity is actually naturally arise, and they do make sense because you can actually compare infinities, as I showed you right now. That if you take two circles, you can actually compare two infinities, and in fact, mathematically, there is a precise definition of comparing infinities also. So, yeah. For example, I will tell you one more. Take take the function x plus 2 upon x square plus 2. Okay. What happens when x goes to infinity? You see that the function in the numerator is linear while the function in the denominator is quadratic. Which one goes to infinity faster? Correct. So what do you expect for the whole function? What will happen to the whole function when you take x? Correct. So infinity does make sense. You can you can approach, you can tell what is the value of the function at x goes to infinity, even though you can never reach that point, but you can still say what will happen at that point. Huh, I agree. Correct. No, even a line is not one dimension. It has some thickness. When you draw a line, it has some thickness. But you think of it as a 1D object. But if you really zoom it, it is not a 1D object. In fact, it's a 2D object. Or also, in fact, it's a 3D object. It might also have some height when you draw a line. So in that, Ah.
How can we compare the integers? Like you said that the x raised to x to the power 3 tends to infinity faster than the other functions.
X plus 2 upon
Like
x.
is there something we can relate, or there is some relation?
You can just check, no, x plus 2 upon x square plus 2. If you put x as 1000, what you get in the numerator? You get 1002. If you put x 1000 in the denominator, you will get 1000 square plus 2, which is like 1 lakh or 10 lakh. 10 lakh 2. So you have 1000 upon 1 lakh 2. If you keep on doing this, if you put x as large number, you see the denominator will always be going faster than the numerator. So actually, when you put x as infinity, denominator will be a much larger infinity than the numerator, and it will suppress it to the extent that the function will become 0. Is it clear? Like, you can think of putting it as
Yes,
large
yes.
number.
Yeah, we can we can assume by looking at it, like this is tends to zero faster than others. But I am just asking, if there are some complex functions, then can we relate?
In general, there is a rule in mathematics. Polynomial always grow faster than logarithmic function. Power laws like exponential, a raised to x, all these kind of function always grow faster than polynomial functions. So if you have ratios of this kind, like for example, if you have log x upon x, then log x goes to infinity with a slower rate than x. So this function will also go to 0 when x goes to infinity. But if you take x over log x goes to infinity faster than log x. So this, no, it's not necessary. It's not necessary. Log you cannot expand if, for example, you can expand log of 1 plus x if x is between -1 to 1. But if x is mod x is greater than 1, you cannot expand it. It's not always necessary that you can. In most cases, you can, but not necessarily for all cases. Yeah, but can you see what is on the slide right now? What do you mean? What do I mean by volume? So the definition of volume is, if I'm in 2D, it means surface area. If I'm in 3D, it means volume, and for higher D, it means hypervolume. So for example, if I have a circle is a hypersphere in 2D. So what is area of circle? It is pi r square. In 3D, a hypersphere is nothing but a usual sphere. Correct? And its volume is 4 by 3 pi r cube. My question is, if you find a general expression for the volume of a hypersphere in d dimension and take that d to infinity, what will happen? My claim is that you will get 0, which is very counterintuitive. Because you would like to think that volume will become infinite, but but it is becoming 0. So that's why I put this here, although it has no connection whatsoever to this talk. But since I was talking about infinities anyway, so I put this. Yeah. I don't think string theories anyway do anything nowadays, because it's not working.
No, they are just teaching something and asking something else.
Yeah, but string theory is still mathematically consistent, although not proven. In to quote Ashok Sen, if it is mathematically consistent, we should not give up on that theory. Maybe we don't have that experimental equipment to test that theory, but someday it might be true that some form of that theory will be realized in nature. So yeah, I always trust Ashok Sen because he's a down to earth person and he has a remarkable understanding of string theory and physics in general. So yeah, respect Ashok Sen.
Salute.
You can ask any question now because talk is over. It was anyway a very small talk. So